The energy is the ability to do work. Did you get that?
Yeah.
All right.
Yeah.
The ability to do work. So, what's the unit of energy?
Newton.
Are you sure? What's the unit of energy? Which is of joules, which is also the unit of work, right?
Yeah.
Because ability to do work. The unit is the joule. The unit is the joule. It's also the unit of work. Or work is a joule. I hope you can see what I'm writing.
Yes, sir.
All right. The symbol is J. Are you listening?
Yeah.
All right. So, you know the different forms of energy. Can you just mention them? Kinetic, gravitational potential, elastic potential. Well, most of these ones we mentioned are under all those potential stuff we mentioned are under stored energy. You know, potential energy involves stored energy, like gravitational potential energy, which is about height, elastic potential energy, which is about changing the shape of an object. Then chemical energy is also stored energy. Electrical energy is also stored energy. You have nuclear energy and so on. Right? So, as we already said, the different forms of energies are potential energy or stored energy, and you can see their list. Gravitational potential energy, elastic potential energy, chemical potential energy, electrical potential energy, nuclear potential energy. They're all stored energies. Right?
Yeah.
They are all stored energies. You know, I told you that you find gravitational potential energy when an object is resting above the ground at a height. You find elastic potential energy or strain energy when an object changes its shape. You find chemical energy in food substances, in fuels, in batteries. You find electrical potential energy when current flows. You find nuclear potential energy in the nucleus of an atom during radiation. Then there's also radiated energy in forms of waves. There are examples under electromagnetic waves. Of course, this is their list in increasing frequency. Gamma ray is the highest frequency. Radio wave is the lowest. But we'll talk more about that, like I said to you earlier. Then you also have sound energy produced when an object vibrates. Then you have kinetic energy or movement energy. Now, these are the forms of energy. Then we can talk about sources of energy, right?
Yeah.
Sources of energy. What are the two main sources of energy? You have renewable energy sources and non-renewable, right?
Oh, yeah.
You have renewable energy sources. Renewable energy sources can be quickly replaced now, isn't it?
Yeah.
Which can be quickly replaced. Can you give me examples?
Solar panel, windmill,
Wind, water.
wind, water,
Okay. Waves, solar,
Wave.
or from the sun. The sources are where you get
from
those
the
energy.
earth core.
Sun, geothermal from the earth core, wind, water where you have hydroelectricity, and so on. Even biomass. You know what biomass are?
Yeah. Wait, no.
Biomass. Biomass are organic materials like wood or even animal remains that you can use for making or producing fuels. Like in Brazil, for instance, they use sugarcane to produce ethanol that can be used as fuel. So I said biomass are organic materials like wood, right?
Yeah.
They are all renewable because they can be quickly replaced. Wood, etc. They are biomass. Okay, then non-renewable.
We have oil, coal,
Coal, oil, non-renewable energy sources. They take millions of years to form and so cannot be quickly replaced, isn't it? So fossil fuels. Fossil fuels, examples are fossil fuels. Fossil fuels. You know, fossil fuels are remains of dead plants and animals that are buried under rocks or mud or under the ocean and acted upon by pressure and heat, and then they turn to fossil fuel. Plants usually change to coal. Ancient vegetations usually change to coal. You know coal now?
yeah,
Then animals and tiny plants in the ocean will eventually change to oil. So fossil fuels like coal, oil, which include petrol, diesel, and so on, natural gas, are non-renewable. All right, that's about that. That's for energy forms and then energy sources. So let's go. It says the drawing below shows a garden of water feature. It is solar panel. It's solar powered. Okay, so we can see the solar power panel or the solar cell.
yes, sir.
We can see the electrical wire connected to a pump which pumps water to the top of this jug, and the water flows down to this bowl, and the water is pumped up again, and then it flows down again, and so on. All right,
Yes, sir.
so the question says the useful energy change in the solar cell is light to electrical. Yes, the useful energy change in the solar cell is from light to electrical. That's correct. Yes, the next one, the useful energy change in the motor is from electrical to kinetic. All right, that's correct.
Yes, sir.
Electric motor is from electrical to kinetic. What about generator?
Yes, sir.
Generator is from what to what?
From kinetic to sound.
Kinetic to electrical.
Sorry, kinetic to electrical. Sorry.
Kinetic to electrical, right? That's a generator.
Yes, sir.
From kinetic sound. Do you turn on your generator to be listening to sound? So okay.
No, sir.
You have a special generator just to hear sound. What do you turn on your generator to listen to get what for useful? Electrical.
Yes, sir.
So it's from kinetic to electrical. Though some generators will start with chemical energy, the fuel, and so on. But the useful energy transformation in a generator is from kinetic to what?
From kinetic to electrical.
Okay. What's the useful energy transformation in an electric motor?
It's from kinetic to
Electric motor, Electric motor.
Pardon?
Electric motor.
It's from electricity to sound. I mean, not to sound, to kinetic.
Electrical energy to kinetic energy is the useful energy transformation in an electric motor. While a generator is the opposite, from
Yes, sir.
kinetic to electrical energy. All right, let's see. As the water flows from the jug, the bowl, as the water flows from the jug to the bowl, it is from gravitational potential energy. Okay, that's correct. Gravitational potential energy, GPE, to is changed to kinetic energy. Kinetic energy, that's correct. All right. So let's see. Then it says, give one advantage and one disadvantage of using a solar cell to power the water feature. It is renewable. What does that mean?
Means that like fossil fuels.
Mm-hmm.
Well, I want a question.
Are you listening there? Give one useful, that's one advantage of using a solar cell.
It is a renewable energy source.
What does it mean for something to be renewable?
It can be used again.
No, it doesn't mean it can be used again. No. It's not what that means. It doesn't mean it can be used again. Renewable does not mean it can be used again.
It cannot finish.
Well, it cannot finish is better, but it's not appropriate. It can be quickly replaced. Did you hear what I said?
Yes, sir.
Let me know if what I've written has shown at your end. It can be quickly.
Yes, sir. It can be quickly replaced.
You know, you can plant trees maybe after a few years to get biomass, you know, like wood is a biomass. But if you have to get another fossil fuel after you have used up the ones you have to wait for several millions of years, isn't it?
Yes, sir.
So that's why fossil fuels are they renewable or non-renewable?
Non-renewable.
Why are they non-renewable?
Because apparently a fossil fuel, you have to wait for millions of years.
It takes a long time to form, several millions of years, so it cannot be quickly replaced, unlike renewable energy sources that can be quickly replaced. All right, that's one advantage. Another advantage is you can say it doesn't cause pollution, or it doesn't cause global warming. You know, it doesn't release dangerous gases that can cause global warming like fossil fuels do. A disadvantage, one disadvantage is it doesn't power out at night. Why? I think you may need to give an explanation, because there's no sunlight.
Okay, so the solar energy only needs the sun to even work.
But
So
there's always there's always sun now.
Yeah, but like the thing during the night, it cannot absorb the thermal energy for the sun because it's
Light is actually light energy. It doesn't power at night where there's no sunlight. Don't say where there's no sun. There's always sun. Or has sun disappeared from the universe now?
Yes, sir.
Oh, the sun has disappeared from the universe now, as we are talking.
No.
There's always sun. In fact, that you're not seeing sun doesn't mean some people are not seeing sun at some other side of the earth. You know, it's just that we are backing the sun now. That's why it's our night time. The people who are facing the sun, they have their daytime. So you don't say there's no sun. You simply say we can't see or we don't have sunlight. All right. So the correct
Yes,
answer
sir.
is it doesn't power at night when there is no sunlight. You understand? Or
Yes,
because
sir.
there is no sunlight at night. It doesn't power at night because there is no sunlight at night. There is no sunlight at night. Okay. So this one's, let me see what you wrote here. I think I need to zoom in, it's too big. Zoom out to capture it fully. Okay, the question says, from the opposite page, give the names of two fossil fuels. All right, coal and gas. What is the source of energy for the solar panel? Sun. Why can't the solar panel work? It needs the sun. And there's no sunlight at night.
Yes, sir.
And there is no sunlight at night. There is no sunlight at night. Okay. What makes the blade of the turbine drawn in go round? Look at the turbine. Oh. This is the turbine they are talking about. Check your Jamboard. The turbine they are talking about is this one.
Yes, sir. Electrical.
If you read it,
The wind.
it's wind, but you wrote electrical energy.
No, I'm sorry. I thought like something was powering the turbine to move. Like I thought it was like a fan.
Okay, so it's actually wind, right? Because it's a wind
Yes,
turbine.
sir.
That's a wind farm, like we call it. Sorry, I've written it.
Oh, sorry.
Okay, this other one. Renewable energy sources will not light run out. From the opposite page, give one source that will not run out. You didn't answer. Well, okay, let me. Light. Do you mean the source? Which source will not run out?
Solar.
Source, the source. They didn't say the form of energy, but the source itself. The source itself.
Oh, the sun.
The sun. Okay, so that's the sun. Sun will not run out.
Yes, sir.
All right. Is that all for this page? Yes. Let me see another one you can answer. We will still meet some other time. Can you go to page 12? Let's just do the one on the middle page. Page 12. Page 12. Answer this one on the middle plane.
Answer this one.
Yeah, the middle page, the middle plane. This one, yes.
Answer.
So it says energy is always changing from one form into another. The diagram below shows the energy changes in a touch, chemical to electrical to heat to light. First of all, before you continue, what's the form of energy stored in a battery?
Electrical. Oh, no, chemical.
Chemical, yes. What's the form of energy stored in fossil fuels?
Chemical.
Chemical. What's the form of energy stored in food substances?
Chemical.
Chemical. So chemical energy you have in all those places. And so the battery, of course, when it is connected to a device with electrical wires, the battery stores chemical energy, so it changes the chemical energy to electrical energy, isn't it?
Yes, Yes, sir.
In fact, the battery changes chemical energy to electrical energy. Okay, continue. When you want to write kinetic energy, you can write KE, okay? Not just K. Kinetic energy,
Okay.
KE. All right. So this particular one that is running down is gravitational to kinetic. That's correct. I'll be marking as you're working. This one is a coal from chemical to heat to light. That's correct. Let me write it in full as chemical. So that's correct, to light. This other one is from light to electrical. That's solar cell. This is from chemical to kinetic. That's from chemical to heat to kinetic. Tuning for kinetic to sound. Okay, that's fine. Can you do the one on the? No. Let me see. I think I have something on page 15. Go to page 15.
Thank you, sir.
Do the whole of page 15.
I've done this before.
Everything on this page?
Yeah, it's on page 3.
Oh, okay. You've done everything on this page. Okay, that's fine. That's good. Let me look at it properly. That's good. Okay. All right. Okay, you've done it earlier. So let me see. I marked it earlier, right? I think so.
Yes.
I think so. If you have done it earlier, I must have marked it earlier then. All right, let's see something else that you're yet to do. Can you go to page 17? Yes, page 17. Page 17.
I haven't done this.
Page 17, right?
Yes, sir.
Okay, let's go to page 17. First of all, let's do this one. This one I'm circling before you continue with the rest. This one I circled. I didn't hear you.
I want it so, but I can see it.
Oh, okay.
This one.
Yes. Let's answer that one first.
Okay.
Because it has something to do with energy before we move on to forces. Okay, it says the diagram shows the energy flow into and out of a coal-fired power station, and this is the coal-fired power station. 100 excuse me, 1000 megajoules in coal, and so on. 70 megajoule wasted in friction. Energy is also wasted in this cooling tower. Another 30 megajoule is wasted in heating wires. 300 megajoule is electricity. So it says how much useful energy is produced by the station. What did you write?
Now 30 million joules.
How did you get 930?
I got this on the station here.
Circle what you're talking about.
I left on the station.
Excuse me. This is the boiler, and you can see that place it is wasted. It's asking about which energy source, how much energy source is provided by the power station. What is the work of the power station?
To give power,
What power?
electric power,
So what is the energy provided by the power station?
electricity.
What is the value of that energy?
300 millijoules.
Megajoules. Okay,
Megajoules.
so how much useful energy is provided by the power station? It should be that 300 megajoules.
300 megajoules.
All right, so correct your work.
Yes, sir.
Okay, let me see. So how much useful energy is provided by the power station? It is 300 megajoule. The reason is the power station produces electricity, which is electrical energy, and that's a useful energy that it provides, 300 megajoules. Let's calculate how much energy is wasted from the cooling tower. This is the cooling tower. How did you get 600?
So 70 millijoules wasted here.
Okay.
So I wrap 1000 millijoules here. So 70 minus 1930.
Okay.
After that, this one took its own for 930, but we don't know to X.
Okay.
So X megajoules. So this one also took its own 30. So you now do 900 minus 30. 930 minus 30, we go on 900.
Good.
And finally, this one we have 300 megajoules here. That was made. So that means to get X, we now do 900 megajoules minus 300 megajoules. We now give you 600 megajoules, which was wasted.
Beautiful. Wasted by the cooling tower. Okay.
Yes, sir.
Very, very correct. It's a correct analysis. So I have to give it to you. Basically, what you said is, since it is 1000 megajoule that is supplied and 70 megajoule is wasted wasted in friction in the turbine and generator, you take it out. What you'll be left with is 930. And then again, another 30 is taken out. You take it out, what you'll be left with is 900. And it is 300 that is produced. You take it out, that means 900 minus 300. It is 600 that will be left. So it is that 600 that must have been wasted by the cooling tower. Okay, that's correct. That's correct. Can you go to this before we leave this issue of energy? Can you go to this question that has a house in it?
Okay, sir. My jump board close.
Okay, so wait for it to reload. This question that has a house.
Okay, sir.
I should be getting ready to release you. Okay, go ahead. I'm mindful that you need to be released very soon. Let's see what we can do for a few more minutes, and then I will let you go.
Yes, sir.
All right. It says name two labeled parts. Okay, let me zoom it in. It's tiny. No, it's much smaller. Let me see how it comes out now. Says the diagram shows a house that uses renewable and non-renewable energy sources. We have all this. Says name two labeled parts that use renewable alternative energy source. So wind turbine, that's correct. Solar panels, that's correct. Says which of the electricity we use is generated by burning coal, which is a fossil fuel. What's a fossil fuel? Much of the electricity we generate is a fossil fuel. Okay, what's a fossil fuel? It's a non-renewable energy source that. Okay.
Since I want to change my answer for
Okay.
BII.
Okay, go ahead. Okay, it says, let me address this one you just changed now. Explain why it is important that we find alternative sources of energy rather than rely on coal. It says it will be exhausted very soon. Okay, now if it's exhausted, can it be replaced very quickly? So we can
No,
just.
it should be replaced very quickly.
Pardon?
This is not renewable.
Okay, it will be exhausted very soon, but it cannot be replaced very quickly. So you may need to add that it cannot be replaced quickly. Not even a matter of very quickly. It can't be replaced quickly because it will take several millions of years. So I'll give it to you. Then this one, you were asked to explain what a fossil fuel is. Well, the fossil fuel is a non-renewable energy source dug from the ground. It makes sense, but I will require something more explicit than this. Let me give you this definition. Fossil fuels are fuels formed by remains of dead plants and animals buried underground or mud for several millions of years. Can you read what I wrote?
Okay, sir. Everything I should on my end.
Hold on, fossil fuels. Let me write. I wrote fossils instead. Fossil fuels. Fossil fuels are formed by Is can you go ahead and read it now?
Nobody?
Yes, can you read it now?
Oh no, sir. I'm having my English.
Okay, it's here to
Okay.
show.
It's regressing now.
Oh, okay, I get it. It's here to
Okay,
show.
so fossil fuels are found by remains of dead plants and animals buried under the ground for several millions of years.
Yes, fossil fuels are formed by remains of dead plants and animals buried under the ground or under rocks for several millions of years. So that's better, right?
Yes, sir.
Okay.
Yes, sir.
All right. I will not keep you for too long. Let me know the first few questions you can easily answer, and then we start rounding off. Let me see. Zoom in. A few more questions to answer. Which one can you answer now? Okay, let's answer this one. This first one. This first one on the left hand side.
Well, since I say this one,
On the yes, answer it.
yes, sir.
This one is about forces. So let's answer this one. Okay. I would suggest that you use a simple term like a force meter, because it's pulling it. You could just use a force meter to measure the. Yes, a tribometer can measure the coefficient of friction, but a force meter is a simple material you can use by just pulling it. Force meter, or if you like, spring balance. Because it wants to measure the frictional force, not necessarily the coefficient of friction. Hassan repeated the measurement for each surface 3 times. Explain why, to make this experiment reliable. Calculate the average mean force for the glass experiment. For the glass experiment, we add this to this to this and divide by 3 average. So 9.3 plus 9.6 plus 10.3. Mean means, another word for mean is average divided by 3, and to find the average you add up and divide by the total number of data. Your answer is circle the one anomalous reading in the table. Anomalous is the one that is completely far from others. The anomalous reading in this table should be, let's check, for each particular surface. Like Capri, we have 24.5, 32.6, 26.4. This 32.6 is far from the rest for this particular value set. 9.3, 9.8, 10.2. That means they are close. 15.0, 18.1, 16.4, not so bad. 32.6 should be the anomalous reading. So that's the one we should circle. It's 32.6 Newton. Okay, I think we can end with this.